Hi Math Studies students, this is Mr. Chen, and we're going to be talking about the limitations of our chi-squared test of independence, and this is part 3 in our discussion on chi-squared. Alright, so let's talk about the limitations here. Just as a note, this information or this video is not going to be required on the test. So the information that you get from this video will be used to help you interpret your data and do better on your mathematical exploration. So just keep that in mind as you listen to this. This is not urgently needed for the test, okay? Alright, so the chi-squared test that we've done so far is used to show whether two variables are independent or not, but there are some situations when we need to make some adjustments because they might give us a false conclusion. Alright. The first one is the first situation when we need to make some adjustments to our chi-squared test is when we have an expected frequency table and some of the cells, some of the expected frequencies are less than 5. Okay, so if any of them are less than 5, generally we might need to make some adjustments. The second situation is if our table is too small. So if our degrees of freedom is 1, for instance, if I have a 2 by 2 table, that's generally too small, and so we might get an error when we make our conclusion. So this lesson is going to be talking about how we can fix that, okay? How we can deal with these types of situations. So let's look at the first situation. If an expected frequency in one of my tables is less than 5, what do we need to do? Okay, and here's the solution. It says this right here, but let's consider an example first. So we have this contingency table, right? We have this table. The chi-squared value when we put it into our calculator is 8.52. All right, so that's our calculated value. If the problem asks at a 5% significance level and a critical value of 7.81, let's say it asks, are the variables independent or dependent? And it looks like whether they're looking at the variables are gender and how often someone watches TV. Is there a link? Okay. So if in this case, this is our contingency table, when we make an expected frequency table, it looks like this. All right, so we end up with these. These are the values that we would expect if this was truly an independent scenario, okay, if our variables really were independent. So our chi-squared calculated value, which is 8.52, is bigger than our critical value. Okay, this, remember, we said is found from our table or from the question it's usually given to you. So in this case, our chi-squared calculated value is bigger. 8.52 is bigger than 7.81. So we can say that because the difference is too large, it's therefore not close. These are not closely related, so it cannot be independent. So we say we reject our null hypothesis, and we say that gender and television watching are dependent. Okay, so that's our conclusion based on this data. But this could be wrong because we said before that if an expected frequency is less than 5, we need to do something about that. Okay, and so let's look at these values right here. Our expected frequencies are actually less than 5. We have one that says 4.05 and one that says 4.95. Okay, so here's the solution. When you get this kind of situation, we need to combine columns or rows. Okay, so we need to combine adjacent rows or columns in our contingency table. So we need to do something to this contingency table to fix this, and the solution is to combine the rows or columns as long as it makes sense to do so. So here we say rarely, sometimes, and often or very often. These are sort of similar, right? So what we're going to do is we're going to combine these. Combine them, and we make a new contingency table. So we have a new contingency table. We've combined often and very often. So basically we're adding more data values in here. Okay, and that will make our chi-squared test of independence a little more reliable. And so when we do this, we get a new expected frequency table. And if we put this into our calculator, we now have a chi-squared calculated value of 4.18. Notice that my dimensions have changed, so my degrees of freedom is also different. My degrees of freedom is now 2, but my significance level stays the same. All right, and the critical value then, based on my new degrees of freedom, is 5.99. This is what I found. This is what I would get from a table. All right, and now let's compare our calculated value with our critical value. You should see that the calculated value is less than our critical value, and so our conclusion is different. Because the difference is smaller than my critical value, we can say that the variables are independent. And so we would accept h sub 0. We would say that they are indeed independent. Okay, so you can see that the conclusion has changed. Okay, up here, the conclusion was that they were dependent, but here that they're independent. All right. So this again is when an expected frequency is less than 5. We need to correct it. We need to make a change to our contingency table by combining the values in our rows. Notice that we added these two to get here. Okay? Remember, it must make sense. So when you're doing your exploration, don't do something like I'm going to add rarely and often together. You know, that just does not make sense. Okay? Or I'm going to add male and female together. That would defeat the whole purpose of this experiment. So just keep that in mind as you do your exploration. Okay, the second situation where we might need to make some changes to our chi-squared test is when our degrees of freedom is 1. Okay, so that means when our size is so small that we end up with a basically like a 2 by 2 contingency table, and so our degrees of freedom is 1. If this is the case, our solution is to use something called Yates continuity correction. Okay, really all this is they're going to subtract 0.5 from this difference. Okay, so if you remember, if you look back at the way to calculate the chi-squared value by hand, okay, you'll see that this part is the only part that's changed. But if our degrees of freedom is 1, then we have to put this in. Okay, that's called Yates continuity correction, and it's a statistical way of fixing a possible error. Okay, I know it's not very intuitive, but this is the formula. You just have to know it and just make sure that you can do this on your math exploration. All right, so let's talk about what this means. This is the absolute value of the difference between our observed value and our expected value. So normally we would leave this, we would just take this part and just square that. But when our degrees of freedom is 1, we have to subtract 0.5 from each difference. So let's take a look at an example to get a better picture of what we're doing. Okay, 80 people were surveyed to find whether they enjoyed surfing and skiing. The results are shown alongside. So here's our contingency table, and the question is, test at a 1% level whether there's an association between whether a person enjoys surfing and enjoys skiing. Is there a relationship? Okay, and this was a survey that was taken. So let's try this. We first start by stating our null hypothesis. Our null hypothesis is, remember, always saying that our two variables are independent. So enjoying surfing and enjoying skiing are independent. Our alternative hypothesis, or H sub 1, the variables are not independent. Okay, so now we've defined that. We need to create our rejection inequality. And in order to do that, we need to look at our table to find our critical value. But before we can find our critical value, we need to look at our significance level and our degrees of freedom. We have our significance level here at 1%. That was given to us. The degrees of freedom is 1, because 2 minus 1 times 2 minus 1 is 1 times 1. So that's 1. We can find our critical value from our table, which is 6.63. And then we set up our rejection inequality. This inequality says if our chi-squared calculated, when we take the chi-squared of this table, if that number is bigger than 6.63, we will reject H naught, or H sub 0. So that's our rejection inequality. So we have to find our, look at our contingency table and make our expected frequency table. So we're going to look at our sum values, right? We take this, we find the sum of each row, the sum of each column, the total sum, and then we find our expected frequency table. But the problem is our degree of freedom is 1. Okay, so normally we would just go ahead and keep going here and find our chi-squared value and then compare that and make a conclusion. But because our degrees of freedom is 1, it's so small, it's 2 by 2, what we have to do is we have to now calculate using our new formula. So let's try. Okay, so we have to use our chi-squared value using our continuity correction. So this actually requires a little bit of calculation, and if you do this, I'm pretty sure you'll get high marks on your mathematical exploration if you use the Yates continuity correction. Alright, so this is our table. We first list our observed values from our contingency table. We list our expected values, right? Notice that they have to correspond. So if I write 8 in the third row, I have to write 15 because it corresponds with 8. We take the difference, we find the absolute value of that difference. Then we subtract 0.5 from it. And this is, it's not intuitive again, but it is part of the process of applying this, and I'm just going to have to say accept it and let's just run with it. Okay, so 0.5, we subtract that from our difference. Then we take this value and we square it. Okay, so if you square 6.5, if you do 6.5 times 6.5, you get 42.25. You get all that. Then you take each of these numbers, okay, and divide it by FE. Alright, we're going to divide this value by this value, and so that becomes 4.225 for the first row, and so on. Okay, and then the Yates continuity correction formula says add all of those up. And if we do that, we get 10.242. Now this is what? What is that? Again, you need to remember this is finding our chi-squared value. So this is our chi-squared calculated value after correction. Okay, so our chi-squared value is 10.2 because we round to 3 significant figures. And then we can make our conclusion. Because our chi-squared value after correction is bigger than 6.63, we are going to reject H sub 0 because we obviously can see that the difference is so big that it's going to be dependent. So it's bigger than our critical value, and our conclusion is at a 1% significance level, the variables enjoying surfing and enjoying skiing are dependent. Okay? So that's an example of how to use the Yates continuity correction when you're doing your math exploration. I would encourage you to try some of these practice problems. There are more in the book, but these are the two that I'd like you to try just so that you have some practice for your exploration. Okay, and that will be it for this lesson. All right, hope that makes sense. Please let me know if you have any questions. Thank you.